Our core topic for today is a theorem that, on the one hand, may seem entirely trivial, but on the other hand, has some surprisingly profound consequences. The pigeonhole principle considers finite sets and a function that maps between them, and applies the properties of functions that we defined last time. If the function that maps a to b is 1 to 1, then by definition, no element of b is the output for multiple distinct inputs. So for f to map every element of a to a distinct element of b, there must be at least as many elements in b as there are in a. On the other hand, if the function that maps a to b is onto, then that means that every element of b is the output of the function for some input. So there must be at least as many elements in the input set in order to produce all of those outputs. And if the function being 1 to 1 means the output set is at least as large, and the function being onto means that the input set is at least as large, then if the function is both 1 to 1 and onto, we can conclude that the sets have the same cardinality. The name for this principle comes from the idea of a pigeon coop, where some number of pigeons live in some number of holes. And so if we have p pigeons being placed in h holes, then we can think of the function that maps pigeons to holes if there are more pigeons than holes, then it must be the case that some hole contains multiple pigeons. In terms of the function, when the size of the input set is larger than the size of the output set, there must be some output that is hit by multiple inputs. So this statement is the contrapositive of 1. A is greater than b is the negation of our conclusion, and if there is some hole that contains multiple pigeons, then our function from pigeons to holes is not 1 to 1. On the other hand, if there are more holes than pigeons, then we don't have enough pigeons to put one in every hole, and so there must be some hole that contains no pigeon. And this is the contrapositive of number 2. If the size of the output set is larger than the size of the input set, that's the negation of this conclusion, that implies the negation of the hypothesis. So that means that the function is not onto, meaning that there are some possible outputs that are not hit by the function, so there's some hole that doesn't get a pigeon. And similarly, the only way that we could have a bijective mapping that is exactly one pigeon in every hole is if the number of pigeons and holes is equal. And so for completeness, the contrapositive of this statement is that if the sets are not of equal cardinality, then there cannot be a bijective function between them. So this simple idea about pigeons in holes and the corresponding principle about when a function could be one-to-one or onto has some very useful applications in counting problems. If I asked you to pick out 27 words from your favorite text written in the standard English character set, then if we think about what letter those words start with, among the 27 words, it must be the case that at least 2 words start with the same letter. Here the pigeons are the 27 words, and the holes are the 26 letters of the English alphabet. And because we have more pigeons than holes, there must be 2 pigeons in the same hole, so there must be 2 words that start with the same letter in any collection of 27 English words, no matter which words we choose. If I gave you 5 points on the surface of a sphere, then, no matter how evil I was in picking out the 5 points, then it should always be possible for you to cut the sphere in half, that is, into 2 hemispheres, such that 4 of the 5 points are on the same hemisphere. The key here is that you can cut the sphere directly on one or more of the points, and then that point is on both hemispheres. This works because we can start by choosing any 2 of the 5 points to lie on the plane that we will use to cut the sphere in half. And since those 2 points are in both hemispheres, then we have 3 points remaining that are spread across the 2 hemispheres. And so by the pigeonhole principle, with 3 points on 2 hemispheres, we must have one of the 2 hemispheres with at least 2 points. And so including the 2 points on the cut, we have 4 points on that hemisphere. In these cases, the pigeonhole principle directly gave us our result, but next we'll look at an example where we will need to use the pigeonhole principle as part of a larger proof. This theorem concerns sequences of distinct integers. So by a sequence here, we just mean a list of integers. And a subsequence is a list formed by deleting some elements from the original sequence. So we're thinking about a list of integers that are all distinct, and then we are going to delete some elements of that list to give us a subsequence. And we are interested in subsequences that are monotone. So monotone means that they are either all increasing in order or all decreasing in order. And the claim is that no matter how we rearrange the elements of the list, this is for any sequence, so any way we could order the elements, it must be the case that there is a monotone subsequence of n plus 1 elements if our original sequence had at least n squared plus 1 total elements. So we'll call our sequence S, and it contains n plus 1 elements, all of which are distinct integers. And we will suppose, towards contradiction, that there is no monotone subsequence of length n plus 1. Now, let's think about the elements of this length n squared plus 1 list, and let's label those elements based on how long of a monotone sequence we can produce starting at that element. So we'll label an element with the number of decreasing elements we could find in a subsequence that starts there, and with the number of increasing elements that we could find in a subsequence that starts there. So the label for the ith element has two numbers. U for upwards denotes the length of the increasing sequence that we could make if we started from I, and D for downwards is the length of the longest decreasing subsequence that we could make starting from the ith element of the list. Now if we consider what values these labels U and D can have for any given element, we know that they must be at least 1, because we could always have the sequence of one integer starting at that position. And we know that they must be at most n, because we hypothesized that there was no length n plus 1 monotone sequence. So that means that the longest monotone subsequence, whether it's increasing or decreasing, must have length at most n. Then, if we have at most n possibilities for U and D, then the label, which is a pair U comma D, must have at most n squared possibilities. And if there are only n squared distinct labels, and we have a length n squared plus 1 sequence, then there must be two elements of the sequence that have the same label. Since I've run out of room, I'm going to erase the top portion, but if you need to refer back to it, you can always rewind. By the pigeonhole principle, there must be two positions in the sequence that have the same label, so we'll call the smaller of those two positions J and the larger one K. And since our labels consist of a U and a D for each position, if those positions have the same label, then they must have the same U and D. But because our sequence consists of distinct integers, we know that the integer at position J and at position K must be different. And so, because these integers are not equal, we have two cases. It could be that the jth element of the sequence is larger, or that the kth element of the sequence is larger. Well, if the jth element of the sequence is larger than the kth element of the sequence, then let's think about the decreasing label for k. If we take the longest decreasing subsequence that started at k, that subsequence had the jth element among those that were deleted, but we could create a longer decreasing subsequence by not deleting the jth element, and so we would have a length dk plus 1 decreasing subsequence starting at position j, which contradicts our conclusion that dj and dk are equal. Or in the case that the jth element was smaller than the kth element, we could lengthen the increasing sequence by starting with the longest increasing subsequence from position k. We could add element j onto it and get a longer increasing subsequence, which would mean that uj is larger than uk. And that contradicts our claim that uj and uk were equal. So either way, whether the jth element or the kth element was larger, we end up with a contradiction. So because we arrive at a contradiction either way, some assumption we made must have been faulty, and the only potentially faulty assumption we made was that the sequence contained no monotone subsequence of length n plus 1. So here, the pigeonhole principle helped us in establishing our contradiction by showing that there must be elements with the same label if we have enough elements, and therefore that when we label everything, we must find a label that indicates a long enough monotone subsequence. So it's great that the pigeonhole principle can sometimes help us in counting problems or in proofs. But the really profound part of the theorem from the start of the lecture is the connection between bijections and cardinality. Part 3 of our pigeonhole principle said that if we have finite sets A and B, and some bijective function that maps A to B, then we can conclude that A and B have the same cardinality. But we can easily argue that this implication actually goes both ways. If you gave me two finite sets, A and B, with the same cardinality, then I could construct a bijective mapping between them. Because both sets have the same number of elements, I could just list out all of the elements in order, and then make those two lists into the columns of a function table. We know that mapping is a function because it would give exactly one output for every element of A, and we know that function is one-to-one and onto because every element of B would be the output of the function exactly once. So whenever you have two sets of the same cardinality, there must be some bijective function that maps between those two sets. So the really awesome idea is that we could redefine our notion of cardinality in terms of bijections. So this definition says that two sets have the same cardinality when there exists some bijection between those sets. And because of the pigeonhole principle, that corresponds to our notion of cardinality for finite sets. But I didn't write finite in our definition here. So let's think about what happens if we extend this idea of bijections giving us equal cardinality to infinite sets. So now, with this definition, we could compare the cardinality of the natural numbers to the cardinality of the even natural numbers, and I claim that those two sets have the same cardinality. We prove that by giving a bijection between these two sets. I claim that f of x equals 2x is such a bijection. So we need to verify that this is a function, that it's one-to-one, and that it's onto. For it to be a function, it needs to have a defined output for every possible input. Well, yes, this is well defined for every element of the natural numbers, and it always gives us something in this set. For it to be one-to-one, we need to have no two inputs that give us the same output, and that's the case because if I gave you x and y that were not equal as input to this function, you would get 2x and 2y, which are not equal, as output. For it to be onto, we need that every element of the output set can be produced as an output of the function. And that's the case because every one of these even numbers in the output set is equal to 2 times x for some x, so it can be the output of this function. And so we have given a bijection between the natural numbers and the even natural numbers, and so we have shown that these two sets have the same cardinality, which might at first be a little bit mind-blowing. We are saying that in some sense there are just as many even natural numbers as there are natural numbers. But this only makes any sense because both of these sets are infinite, so we cannot actually count all of their elements. The only way that we could establish whether they have the same number of things is to create a bijective mapping between the sets. Let's do another example. So here we are claiming that the natural numbers and the set of pairs of natural numbers have the same cardinality. And again, we prove it by giving a bijection between these two sets. So let's start by thinking about how we can enumerate all the possible pairs of natural numbers. Well, the Cartesian plane gives us a great way of visualizing pairs of integers. If we lay out the points in the first quadrant of the plane that correspond to integer coordinates, then we will have listed all of the pairs of natural numbers by plotting them on the plane. And so now we want to build a function table where we map the natural numbers to pairs of natural numbers. And so we could list out the natural numbers in order for the left-hand column of our table. And then we could fill in the right-hand column of our table by specifying our ordering according to some path through the plane that is guaranteed to eventually enumerate all pairs of integers. And so we could define a path where we snake back and forth between the x and y axes going along successively further and further out diagonals. And so this path will eventually, if we follow it far enough, hit any integer coordinate point in the first quadrant of the plane. And so we can then list out these points in the order they appear on the path. And so, by defining this function table, we have given a mapping from integers to pairs of integers. And so, every integer has some corresponding output, so we have succeeded in defining a function. And now we ask whether that function is one-to-one and onto. For it to be one-to-one, it must be the case that no pair appears more than once in the right-hand column, but as we follow this path, we're always getting progressively further away from the origin. We're never coming back, and so we're never going to repeat a pair, and so nothing is going to appear twice. And if we follow this path far enough, we will eventually get to any pair of natural numbers. So, since every possible output eventually appears, this function is also onto. So our function is a bijection between the natural numbers and the pairs of natural numbers, which means that by our definition, those two sets have the same cardinality. But we should also consider the opposite case. When can we have infinite sets that don't have the same cardinality? Is it always the case that any two infinite sets can have a bijection between them? It turns out that the answer is no, and this gives us a chance to show off one of the most famous examples of a proof by contradiction. One variant of Cantor's theorem says that the cardinality of the natural numbers is not equal to the cardinality of the 0 to 1 interval of real numbers. So we are hypothesizing that we have some bijective function that maps the natural numbers to the 0-1 interval, and then we're going to arrive at a contradiction by showing that we missed something in this interval, meaning our function wasn't onto and therefore wasn't a bijection. So once again, we will define our function by writing down the function table. But since our goal is to show that there can be no such function, we're going to write down a generic function table for any possible function that would map the natural numbers to the interval. Any such function would have to have, in the right-hand column, a bunch of decimal expansions of real numbers. And since we're talking about the interval from 0 to 1, all of these function outputs must start with 0 point something. Let's make our lives slightly easier by making this an open interval. And since we're going to show that the open interval is in fact bigger than the natural numbers, then also adding in 0 and 1 to make the interval closed will also clearly be bigger. So now we know that the decimal expansion of every number has to start with 0 point something, and some of those decimal expansions must go on forever. So, to make our lives easier, we can represent all of the numbers in the output column here by an infinitely long decimal expansion. If a particular output of the function is 0.2, then we could represent that as 0.20000 ad infinitum. So that means that every entry in this right-hand column has some string of decimal digits going off to infinity. And so we don't know what those digits are since we're thinking about a generic function, but we know that there must be some string of digits. And we will label those digits with a double subscript, where the first number in the subscript represents which row of the table we're in, and then the second subscript indicates the column. So, for every entry on the right-hand side, we have some sequence of digits. That sequence is infinitely long, though at some point it may turn into repeating digits, but we can still keep writing those digits down indefinitely. And so now I want to show that there is some number that is part of this interval that is never an output of this function. And I can do that by specifically constructing a number that is different from every single entry in the right-hand column. Since our numbers have an infinite number of digits, I can make a number where for the ith digit of my number, it is different from the ith entry in this table. So I will construct the number where I define the digits of my number in terms of the digits of whatever numbers happen to appear in this table. So if you gave me some function that mapped the natural numbers to the real interval, then I could look at your function table, and in the entry for 0, I could pick a digit that is not equal to digit 0 of that number, and then I could pick a digit 1 of my number that is not equal to digit 1 of the entry for 1 in the table. And then I could make sure that digit 2 of my number is different from digit 2 of the number that your function maps 2 into, and so on. And so, in the infinite string of digits that defines my number in the 0-1 interval, I will ensure that my number differs in at least one position from every single entry in this table. I could do this by incrementing the number in the table and looping around if I go over 9. But as long as I pick some entry for each digit that differs from the corresponding digit of each entry in the table, I have chosen a number that is in the 0-1 interval that is not the output of the function. And since the way I constructed this number only relied on the fact that I was given a function, it didn't rely on anything specific about how that function worked, I can do this for any function that you gave me from the natural numbers to the 0-1 interval. And that means that for any such function, it is possible to construct a number that is never the output of the function, and therefore there is some element of the output set that isn't hit, and so the function cannot be onto. And so because we could construct a one-to-one function from the natural numbers to the 0-1 interval, I will leave it to you to construct such a function, but we cannot construct an onto function, we conclude that this set must be strictly larger than this set. So that means that among infinite sets, we can sometimes prove that they have the same cardinality, and we can sometimes prove that they have different cardinality. And this proof technique, known as diagonalization, because we walk down the diagonal of this theoretical infinitely long function table, is extremely useful when dealing with infinite sets. And if you take theory of computation, you will see this diagonalization proof technique in what is the founding result of computer science, that the halting problem is undecidable.